A matrix is a rectangular array of numbers. The numbers in the array are called entries. The size of a matrix is the pair of numbers, the number of rows and the number of columns. Matrices are used to describe linear equations. In economics, various situations are represented in the form of matrices. For example, transportation problem, Cramer's rule involving determinants, is used for searching an optimal solution for cost-related problems. Hessian determinant of a matrix composed of all the second-order partial derivatives is also used in optimization problems. The individual items in a matrix are called as elements or entries, provided that they are the same size, have the same number of rows and same number of columns. Two matrices can be added or subtracted element by element. The rule for matrix multiplication, however, is that two matrices can be multiplied only when the number of columns in the first equals the number of rows in the second. Any matrix can be multiplied element-wise by a scalar form its associated field. A major application of matrices is to represent linear transformations, that is, generalizations of linear functions such as fx is equal to 4x. For example, the rotation of vectors in three-dimensional space is a linear transformation which can be represented by a rotation matrix R. If V is a column vector, a matrix with only one column describing the position of a point in the space, the vector RV is a column vector describing the position of that point after a rotation. The product of two transformation matrices is a matrix that represents the composition of two linear transformations. Another application of matrices is in the solution of systems of linear equations. If the matrix is square, it is possible to deduce some of its properties by computing its determinant. For example, a square matrix has an inverse if and only if its determinant is not zero. Insight into the geometry of a linear transformation is obtained along with other information from the matrix eigenvalues and eigenvectors. Application of matrix mathematics. Matrix mathematics applies to several branches of science as well as different mathematical disciplines. Let us start with computer graphics, then touch on science and return to mathematics. We see the result of matrix mathematics in every computer generated image that has a reflection or a distortion effects such as light passing through rippling water. Before computer graphics, the science of optics used matrix mathematics to account for reflection and for refraction. Matrix mathematics help us calculate the electrical properties of a circuit with voltage, amperage, resistance, etc. In mathematics, one application of matrix notation supports graph theory. In an adjacency matrix, the integer value of each element indicates how many connections a particular node has. The field of probability and statistics may use matrix representation. A probability vector lists the properties of different outcomes of one trial. A stochastic matrix is a square matrix whose rows are probability vectors. Computers run Markov simulations based on stochastic matrices in order to model events ranging from gambling through weather forecasting to quantum mechanics. Matrix mathematics simplifies linear algebra, at least in providing a more compact way to deal with group of equations in linear algebra. After studying this module, you shall be able to understand matrices, learn to find sum and product of two or more matrices, identify symmetric, skew-symmetric, diagonal, upper triangular and lower triangular matrices, understand trace and transpose of a matrix. Let us discuss about matrices. An array with m rows and n columns is referred as a matrix. It is generally denoted by a capital letter like A, B, and so on. The m rows and n columns is called as dimension of a matrix. The matrix with one row is called a row vector. A matrix with one column is known as column vector. The entry of a matrix A which stays in the ith row and jth column will usually be denoted by Aij or Aij. Graphic uses of matrix mathematics. Graphic software uses matrix mathematics to process linear transformation to render images. A square matrix, one with exactly as many rows as columns, can represent a linear transformation of a geometric object. If the video game has curved deflecting surfaces such as a shiny silver goblet, the linear transformation matrix would be more complicated to stretch or shrink the reflection. Matrix applications. Matrix mathematics has many applications. Mathematicians, scientists, and engineers represent groups of equations as matrix, then they have a systematic way of doing the math. Computers have embedded matrix arithmetic in graphic processing algorithms, especially to render reflection and refraction. Some properties of matrix mathematics are important in math theory. However, few of us are likely to consciously apply matrix mathematics in our day-to-day lives. Now we will talk about special matrices. Square matrices. A matrix with n rows and n columns is called as a square matrix of size n. Identity matrix. The identity matrix is a square matrix of size n written as In whose all diagonal entries are 1 and non-diagonal entries are 0. Null matrix. The matrix all of whose components are 0 is termed as null matrix written as 0. Diagonal matrix. A diagonal matrix is a square matrix in which all the entries are 0 except for those on the main diagonal, which may be arbitrary. A shorthand notation which lists only the diagonal entries is sometimes used for diagonal matrices. Example: D is equal to diagonal 12 minus 3 1 8 denotes a matrix having 12 minus 3 1 and 8 on the diagonal and rest all entries as 0. Upper triangular and lower triangular matrices. An upper triangular matrix is a square matrix in which all elements underneath the main diagonal vanish, like 1 5 3 0 2 1 0 0 4. A lower triangular matrix is a square matrix in which all the entries above the main diagonal vanish, 1 0 0 2 3 0 4 5 6. Next we will discuss about matrix operations. Two matrices are called equal if they have same size and their corresponding entries are equal. Sum of two matrices and multiplication by a scalar. The sum of two matrices A and B of the same size Mn is this matrix C of size Mn such that Cij is equal to Aij plus Bij for every I and j. In order to multiply a matrix by a scalar, one has to multiply all the entries of the matrix by this scalar. Properties of matrix addition and scalar multiplication. A plus B is equal to B plus A. A plus bracket B plus C is equal to A plus B bracket plus C. K multiplied by A plus B is equal to Ka plus Kb. X plus y whole multiplied by A is equal to Xa plus Ya. X bracket Ya is equal to Xy bracket A. K bracket AB is equal to Ka bracket B. Ak bracket B equal to A bracket Kb. Multiplication of two matrices. Let A be a matrix of size Mn. Let B be a matrix of size Nk. The number of columns in A is equal to number of rows in B. The product of A and B is a matrix C whose size is Mk such that Cij is equal to Ricj. Cij is a product of the row vector Ri and the column vector Cj. That is, Rc is equal to R1C1 plus R2C2 plus so on till Rn-Cn. Example: 224 multiplied by 135 is equal to 2 into 1 plus 2 into 3 plus 4 into 5, which is equal to 2 plus 6 plus 20, which is equal to 28. Note: if matrices A and B are such that the number of columns of A is not equal to the number of rows of B, then the two matrices cannot be multiplied. Properties of matrix multiplication. A bracket BC is equal to AB bracket C. A bracket B plus C is equal to AB plus AC, which is equal to A plus B bracket C, which is equal to AC plus BC. 1A is equal to A. 0A is equal to 0. Here, the 0 on the left is the number 0. The 0 on the right is the 0 matrix of the same size as A. That is, a matrix all of whose entries are 0. Let In denote the identity matrix of order n. Then, In cross A is equal to A cross In, which is equal to A. Transpose of a matrix. For any matrix A m cross n, the transpose of A denoted by At is the n by m matrix obtained by interchanging the rows and the columns of A. That is, the first row of A is the first column of At. The second row of A is the second column of At, and so on. Example: the transpose of 1, 2, 3, 4, 5, 6 is 1, 3, 5, 2, 4, 6. Next, we will discuss about the properties of transpose. A transpose transpose is equal to A plus B whole transpose is equal to A transpose plus B transpose. K A whole transpose is equal to K into A transpose. AB whole transpose is equal to B transpose multiplied by A transpose. Trace of a matrix. If A is a square matrix, then the sum of the entries on the main diagonal of A is called the trace of A and is denoted by Ra. Example: the trace of the matrix 7, 2, 6, 3, 4, 5, 1, 5, 6 is equal to 7 plus 4 plus 6, which is equal to 17. Properties of trace. Trace of A plus B is equal to trace of A plus trace of B. Trace of Ka is equal to K times trace of A. Trace of A transpose is equal to trace of A. Trace of AB is equal to trace of BA. Symmetric matrices. A square matrix A is called symmetric if A transpose is equal to A. Aij is equal to Aj for every I and j. Note: if A is any symmetric matrix, then An and A inverse. If A and B are any symmetric matrix, then A plus B is also symmetric. In addition, if they are of same size, then AB is equal to BA. Moreover, AB is symmetric. Skew-symmetric matrices. A square matrix A is called skew-symmetric if A transpose is equal to minus A. Aij is equal to minus Aj for every I and j. Note: in particular, if I is equal to j, then Aii is equal to 0. That is, the diagonal entries of a skew-symmetric matrix are 0. Every square matrix is the sum of symmetric and a skew-symmetric matrix. Lastly, we will be discussing about determinant of a matrix. Determinants are defined only for square matrices. A determinant is a real number related with every square matrix. For the 2 cross 2 matrix, it is the difference of product of off-diagonal entries from the product of diagonal entries. A is equal to A, B, C, D. That is, determinant of A is equal to AD minus BC. For a 3 cross 3 matrix, it is given by A is equal to A, B, C, D, E, F, G, H, I. The determinant of A is equal to A multiplied by EI minus FH minus B multiplied by DI minus FG plus C multiplied by DH minus EG. Let us now summarize what we have learnt in this module. A matrix is a rectangular array of numbers. The number in the array are called entries. The size of a matrix is the pair of numbers, the number of rows and the number of columns. An array with m rows and n columns is referred as a matrix. It is generally denoted by a capital letter like A, B and so on. The m rows and n columns written as m cross n is called the dimension of a matrix. Two matrices are called equal if they have the same size and their corresponding entries are equal. A square matrix A is called symmetric if A transpose is equal to A. A square matrix is called as Skew-symmetric if A transpose is equal to minus A.